Good morning, everyone, and thank you for being on time. Just give me a minute, then we'll start the session. Good morning once again. So, in the last session, we were going through the concepts of risk and CISC as what is reduced instruction set computers, what is complex instruction set computers. Uh, we have seen the applicability as well, where nowadays, whichever be the handheld devices or even the televisions that we are having, or say be the Sony PlayStation or these kind of devices that are becoming popular. So all of them have started adopting the RISC architecture. The only advantage that goes with CISC was the legacy applications that can easily run on CISC because CISC was prevalent right from 1980s. So the applications that were developed utilizing the CISC computing, so that way uh, it was having the biggest advantage. Not only this, many times we need some complex instructions to be executed from the hardware side as well in order to have a better performance, right? Because if something is coming directly out of hardware, then definitely you can judge easily that it will be somewhat on a speedy note, right? So, mm, we have seen the differences. We have seen the utilization of RISC and CISC. Even nowadays in Apple M1, M2, M3, and further computers, we are witnessing risks. Not only that, we have seen that even AWS have started deploying risk architecture through its Graviton series. So through AWS Graviton series, again you are having the risk architecture, right? So after that, we have gone through the hardwired and microprogram control unit. So that was the part of our processor. If you recall the von Neumann model, then within the von Neumann model, we have seen that control unit is a major component that distinguishes or that generates the control signals, and because of which the whole computing plays into action, right? So we have seen that there were two components, there were two types of control unit. One is hardwired control unit, and another one is microprogram control unit. Nothing needs to be remembered. If you go to the verbal meaning, then hardwired control unit, as you can depict that hardwired in the sense that it is somewhat embedded within the hardware itself. The control signals are generated, or what we can say, the control signals are generated, and the whole responsibility goes with the hardware aspect as well, right? So that way it will be quick, fast, right? And not only that, the only problem with hardwired control unit is in case the manufacturer would like to make some changes within the control unit, then it will be somewhat difficult because it is hardwired. While in case of microprogram control unit, definitely there is a basic hardware, and over that basic hardware, the control signals are generated utilizing the microprograms that are being written on the hardware. So at a later stage, in case if some changes are being required by the manufacturer, so he doesn't have to change the whole hardwired system. Rather, he can just change the microprogram and then go with it, right? And I hope that now you people are very clear that in terms of architecture, in terms of organization, who are the stakeholders for different categories. Say it be if some hypervisor writer is there, say it be if some team is there writing the operating system, say it be if some team is there writing the compilers and all. So that way you would be easily able to differentiate as how these different stakeholders are involved in the utilization of computer architecture or computer uh, organization, right? So that way it should be very clear from you about the stakeholders or any specific change, right? So if I say that the addressing bits are being changed, okay, so what will be your purview? Means whether it is a part of architecture or whether it will be part of organization. So these things now I think it is will be clear to you people because I have gone through a configuration yesterday. So my purchase officer shared me because we being a government entity a bit, although Section 8, but somehow related with government. So that's why we have to make the purchases through government e-marketplace, that is GEM. Okay, so my purchase officer just I have enabled the mic, so you can unmute yourself. So he just asked me that, okay, this is a system that we are getting. So can you please evaluate? So when I have gone through the specifications, it was written Core 7, right? But it was not equivalent to Core i7 because that was just another category of Core series. But it was Core 7 rather than Core i7. When I deep dive into the specification, I came out to know that the number of cores, the cache size and all, that was somewhat specific to i5 processors, right? So that cannot be considered equivalent to I7. So that time I just realized that, okay, now I think you people also might have the vision towards looking at the processor of a computer, looking into the efficiency core, you're looking into the performance core, right? And we have gone through addressing modes as what exactly are the different addressing modes, direct, indirect, and several other addressing modes we have gone through. Okay, and within that, there was a discussion as how exactly we can decide on a specific addressing mode being used. Say it be if add instruction is there, and along with add instruction, if some operands are being given, so how the system will be knowing that which particular addressing mode is being utilized or is to be utilized, right? So that way, I have downloaded this Intel 64 and even IA32 architecture software developers manual, right? So mm, if you see the index, then a lot of things are there. So basically, it starts with the basic arithmetic like bit and byte order, hexadecimal and binary number. segment addressing. Later on, history is there as the whole Intel history, right from 286, 386, 486, then Pentium, Celeron, then Xeon, right? So you can go through the history and basic execution, say it be the modes of operation. What do we mean by 32-bit? What do we mean by 64-bit? Then operand addressing, how instruction pointers are being taken, how the data types are being utilized, instruction set summary. So this section talks about the various binary arithmetic instructions, shift and rotate instruction. So those who would really like to deep dive into it, I'll share this manual and you can go through it. It's very exhaustive. Means you can even say that if we have to do the programming, then support is being there. Various technologies, say it be Intel streaming SIMD or programming with Intel's MMX technology. So I think it is a Bible kind of thing as far as the processor is being considered, right? So it's ample, it's huge, right? So you can see that transactional, synchronizational extension. So all these programming can be done. Apart from this, one white paper I have seen related to multi-core architecture, where how the Intel Atom processor and at a later stage we will be having multi-core architecture, say it be the dual core, quad core later on. Now it's not dual core or quad core. Now we are having much more cores. So that's why nowadays you don't have to listen those words like dual core and quad core. So those who are using the system from 2010 or so, so you might have heard about this configuration like dual core and quad core. But nowadays, because the number of cores are more than that, and that's why you don't listen, right? So I'll share both of these documents. Now coming back to our module, right? So we have gone through the pipeline processor as well. The basic concept we have already seen. But before that, since the main logic that we were discussing in the last session, right? So we will just make it somewhat clear so that the people, those who were keen enough, I think Yuvraj and Gautam was there. So we will just have a look as what exactly will be the case in terms of this hardwired in terms of that addressing modes, right? So I think you remember that, okay, what exactly is register addressing, then immediate addressing and all, right? So supposedly we will just have a look. So for your EC2, we will at last we will be having a 5-10 minute session so that whatever be the doubts related to EC2 that may be clear. So if I'm writing add R1 comma R2 or corresponding to the same instructions, if I'm writing add R1 comma 5, if I'm writing add R1 comma 1000, or if I'm writing add R1 comma R2, right? So I think by the notation you may be clear that what exactly these addressing modes are. This is your register, This is your immediate in terms of this 5 because we are providing the value directly. This is your direct memory addressing, mm, where we are providing the address of the variable, and this is register indirect addressing. Right, so this is the case. The instruction is same, but operand access method change. Right, so there can be several methods related to this. Uh, if you see, then one is if you can clearly differentiate the operand, right? So if you can clearly differentiate the operand, say it be if it is register entry or if it is say it be direct entry. So in that case, based on the operand, the specific addressing mode can be processed. Okay, but that is somewhat difficult because if I am writing 5, then whether 5 is the address or whether 5 is, because here we have seen or we have differentiated it from the notation of the square bracket. Okay, so if such kind of differentiation is there within the instruction itself, then definitely we can say that okay, it will be decided by the operand itself. If not, then there can be a measure where we will be having, say it be opcode corresponding to add instruction, then directly we can have the bits reserved for address mode, right? Then for register, as which particular register is there, and finally we can have the operand address. So this may be the case, and you can say that okay, tentatively 6 bits may be used for opcode, 2 bits for addressing mode, 4 bits for register, and say it be 16 bits for operand address. So this can be the case. Okay, so if we are trying to say it for immediate addressing mode. Right. So for immediate addressing mode, I may be writing opcode, whatever be the opcode corresponding to add. For the time being, just assume it is 001011. So 6 bits, right? So for immediate addressing, you may say that okay, addressing mode will be 00. Okay. Then R1, whatever be, suppose we are having 16 registers. So corresponding to 16 registers, whatever be the value, say it be 0011. So I'm referring to, or in case of R1, suppose I would like to refer R1. So I can simply write 0001 as the bit combination, and then I can specify the operand address. So these are the basic things we can do. Okay, on the other hand, supposedly for your addressing mode or for register indirect, you may be saying that okay, addressing mode is 11. So because supposedly there are 4 options, 4 different addressing mode that can be chosen at any time, or the maximum number of addressing mode corresponding to any instruction are 4. Just assume in that case 2 bits will be utilized, and supposedly if it is more, say it be altogether it is 6, right? So in that case here in addressing mode 6 bits will be utilized. Okay, so this was the major concept where we can have a separate bits corresponding to the address mode that is to be referred. And on the practical side, whenever you will be referring the 86-bit architecture or 64-bit architecture, so you can see the manual where in manual itself they are being represented by MOD, right? So what they usually refer that apart from addressing mode, So they are being referred as MOD bits or the mod bits, right? So opcode mod bits. So if you see that file, the PDF that I have shared corresponding to the architecture, then you will come to know that MOD is there, and within that, 00 is there for memory, 01 is for memory and indirect mode, and so on. So that way you can uh, have a look at the various options corresponding to the addressing mode. But I think now the overall thing related to the addressing mode is clear, where we were deciding as what exactly will be the addressing mode utilized based on the operand. Okay. In the last session, we have seen about pipeline processor. This was the basic analogy we have seen, where if we are not using the pipelining, then the things were completed starting at 6 p.m. and will be ending at 12 midnight. While here, in this case, when pipelining was there, where we can execute multiple instructions with a single clock, right? So that way, it started at 6 and completed at 9:30, right? So this was the case, and if we see it from the instructions perspective, so again, make your point very clear that this will be the part of processor, okay, and your say it be your compiler writers, or say it be your operating system, your hypervisor writers, they will be utilizing the concept of pipelining that is available within the processor. At the top level, say it be if you would like to access, means you can access the cores, but as such you cannot directly utilize the pipelining of the processor through the high level programming language. So that won't be possible. Okay. So you can just have a look. IF stands for instruction fetch, instruction decode. Then this is address generator. DF is for data fetch. Please be careful with your mic. Sorry for that. Yeah. So AG is for address generator, DF is for data fetch, and EX is for execution, and WB is for write back. Okay. So supposedly we are having four different instructions. Okay. And corresponding to these four different instructions, if we can create a pipeline and somehow if one instruction is started and at a later stage if another instruction is to begin, right? So then can we have the execution of both the instructions in parallel, say it be in a pipeline mode where the single clock will be utilized for the operations of multiple stages. Say it be at this particular stage, if some clock is there, then for this particular instruction, it will be the data fetch mode or data fetch stage. For this, it will be address generator. For this, it will be instruction decode. And for this one, it will be the instruction fetch. So this way we can utilize the pipelining. But again, the concept should be clear to you that who are the stakeholders, those who will be responsible for utilizing the concept of pipelining for the processor. And if you recall, then when we have seen in during the first few sessions where what are the various ways through which we can increase the performance of the processor. Sorry for this, spelling goes wrong. Okay, so pipelining was one option that we have seen, right? Because ultimately you can just have a look if we can execute multiple instructions. So definitely that would be better, right? So if you can see here that risk architecture, we take example of ARM processor, which is based on risk architecture, it follows three-stage and five-stage pipelining. So these are the two stages that they usually support, right? Different processes may have different steps, but if you see the diagram, then you will be having a look as how exactly the pipeline can be carried out, right? So those who are good at the hardware perspective, though you will be able to easily catch it. But we don't have to go to this level of depth. But at least we should know that for increasing the processor performance and for cloud infrastructure, ultimately we should be able to check the pipelining as whether the processor we are utilizing supports the concept of pipelining or not. So these are all the advantages that we will carry with the concept of pipelining, right? So we will see one by one what are the advantages. Okay, so you can easily assume, say it be instruction throughput obviously will increase because the number of instructions that we will be able to carry out through this will be somewhat more within a stipulated time, right? Increases in the number of pipeline stages, increases the number of instruction executed simultaneously. So whatever be the pipeline that you can create. So this way, if I increase one more over here, right? So this way we will be saying it as a five-stage pipeline. So there can be three-stage pipeline, right? So that way, if we increase the number of pipeline stages, so that way we can have maximum more number of instructions to be executed, right? And faster ALU, that is arithmetic logical unit, can be designed where the results of the arithmetics can be derived on a faster note. And obviously, pipeline CPUs works at higher clock frequency than RAM. Mm, That's quite obvious and increases the overall performance of the CPU. There are some issues in the pipelining that few of you might have already pointed out, that dependency whenever there is some data dependency of one instruction on another instruction, right? Say it be if whatever be the data that is being generated by this instruction. Okay, so if this instruction is generating some data and that data is to be utilized by this instruction, right? In that case, we cannot put these two instruction in pipeline, right? So that won't be possible. And whenever such is the case, pipelining cannot be used. Apart from that, similar cases as that of data dependency, one is the branch instruction where if there is some any branch instruction where the decision is to be made as after the branch, the decision will be made. Say it be if we are having some if kind of a statement where based on the input things will be decided, then we never know where the things will be going, and apparently in such case it will be somewhat troublesome to go for the concept of the pipeline and interrupt operation. Again, if some interrupts can be occurred in between, and which instruction exactly to interrupt. In that case, things will be really difficult in such cases, right? So that way, whenever we are having some data dependency branch instructions or interrupt operations, so these are the examples. So it be data dependency, add R3. So R3 is being used over here in the next instructions. So we cannot put up these in the pipelining, right? Impact on cloud, say it be if the processes are pipelined and if we would like to see that what exactly is the impact of the processor on cloud, then these are all the cases that we can witness if the processes are pipelined, right? So these are many. So we'll see one by one quickly. So definitely increase instruction throughput. We have already seen in
So
case of
sorry to
individual processor as well. Yeah, wait, Patel.
sorry to interrupt.
Yuvraj, sorry. Uh,
Can you just talk about that interrupt handling mechanism and how does it impacts pipelining a bit more?
Again,
I didn't
if
understand
you,
that
yeah,
clearly.
just a minute. Mm, Start with, so if you recall the first few sessions, then there we have gone through the interrupt thing. Just a minute. Now just have a look. Say it be if this is the normal cycle when we go with the instructions, right? And in this case, supposedly, if some interrupt occurs and I just have to put the things on stack or some kind of data structure from where at a later stage, if the interrupt occurs, the operations can be resumed. Right. So if we are using pipelining and at a later stage, we never know how things will be carried out and what sequencing will be followed. So for that particular reason, whenever there is a possibility that okay, interrupts can be there, right? So in that case, the concept of pipelining is usually being avoided, right? You can just have a look, say it be if interrupt happens and somehow if the whatever be the data operations has been done or some data is being fetched. So corresponding to that, I need to put all these in stack, right? And at a later stage, I don't know, means I may have, right? So I may have done it in this way that okay, these five instructions can be taken within the pipeline, considering that everything goes normal.
Mm-hmm. Okay.
Because issues are there, ultimately they are being somehow handled. So if everything goes normal, then this was the case from our side that okay, things will be going in this way. But supposedly interrupt occurs over here corresponding to the second instructions. Now we never know how things will be going. Say it be if interrupt occurs and whatever be the higher priority process is there, so that process will be getting the control, right?
Mm-hmm.
Down the line, whatever be the machine level instruction corresponding to that particular process, those will be loaded, right? How we will be backtracking in this case, right? So that is the main reason why in case of pipeline, if we are utilizing the pipeline, then interrupt is not the normal case, and special measures needs to be taken whenever interrupt will be there, right? So whenever we are having data dependency or other cases that we have seen, ultimately we have to be somewhat cautious while going through the concept of pipelining.
Okay, so the additional stages which we computed, assuming that operation is going to behave in a normal way,
Yeah.
those particular results would be thrown away if interrupt comes into context, right?
So you are saying that if we put it in a stack, then again, whenever it is being resumed, it will be going in the same way. Is that the case?
Okay. Would we
But
be able to put results of each stage into stack? I doubt that particular part. Let's assume
yeah,
this
that's
particular
what I'm
slide.
saying,
Hmm.
that we cannot put the result of each stack, each stage
Pipeline
in the
stage.
stack. Yeah,
Exactly.
pipeline stage. Yeah.
Mm-hmm.
So it's not like that we are not able to utilize it whenever the interrupt is there, because interrupt can occur. We cannot negate that interrupt will
True.
not be
True.
occurring, right? So the thing is, the point worth mentioning over here is there are issues and needs to be handled. Right, so there
Okay.
can be several ways through which the programmers, the low level machine level programmers may be handling it. But because of all these cases, issues are there that needs to be handled in some specific way.
Okay. All right. Thanks.
Okay, yeah. So when we go to cloud infrastructure, definitely means whatever be things applicable on a single processor, definitely that will be applicable on the cloud infrastructure as well. Okay, so you can see that, okay, increase instruction throughput, definitely for cloud as well, it will be the case because ultimately the processor that is being utilized is same. Latency will be reduced, optimal use of CPU resources, that's quite obvious. Energy efficiency will be there because corresponding to single clock, we are able to execute multiple instructions. Scalability, obviously, we are doing parallel processing, so that way, whatever be the number of pipelines available, at least till that level, we can scale, right? Flexibility in workload management. Again, by having multiple stages, we can have the required flexibility, parallel processing. Obviously, we'll be needing some advanced instruction sets corresponding to this, but again, that will be taken care by the processor manufacturer and being utilized by your OS writer, or say it be your hypervisor writer or your compiler writer. And consistency in performance is quite obvious. May not be there in case there are a series of branch instructions also, but mostly you will be witnessing it. Error handling and recovery, right? So what happened is many of the modern pipeline processor, along with the basic functionality, they incorporate error detection and correction mechanism as well, right? So that way, errors are being handled and recovered through the pipeline processor. Now, coming to the concept of multi-core processor, through which we would like to increase the efficiency. Just a minute. Okay. Now coming to just have a look at the word cloud, and most of the things we already have seen, right? So Murray's law we have already gone through. Okay. And again, just put some more attention. Uh, we have seen that processor performance can be increased, and if we increase the density, if we increase the uh, frequency of the processor, so ultimately we will be able to have more speedy operations as far as processor execution is being considered. But the problem that we have faced was the heat dissipation and power consumption increases as we move further, and that's the reason means we have seen it several times that right from 2000 or so, okay, and today it is 2025. Even if you see the Xeon processors, right? So in 2000, I have seen witnessed the frequency of 1 gigahertz. Even in 2025, the maximum frequency that I have seen even in i7 or so, or Xeon processors, because they are somewhat for the server, so they don't come up with the very higher frequency. Say it be, my system is having a maximum turbo frequency of 5.4 gigahertz, right? But if you would see in Xeon, you will hardly find any processor that will be having a frequency of 5.4 gigahertz. This I have checked 6 to 8 months back, right? Because for the same reason, because ultimately, if you keep on increasing the frequency, so the heat dissipation and power consumption will increase. So for fewer cores, so if you are limiting the cores, then in that case, it will be okay to go for some higher frequency similar to that of 5.4 gigahertz. But like in Xeon, where you will be having even the cores will increase. So all the cores having the maximum turbo frequency of 5.4 gigahertz. So things will be troublesome, and that's why you can just give it a try, and we can have a good discussion on this. Just try to see whenever you will get a chance to check any server configuration, right? So supposedly if you see my system's spec, so you can just see that the CPU is operating right now at 2.28 gigahertz, right? So that is the base speed, but 5.4 gigahertz is the maximum to which this particular processor can go. Okay. And if you see the Xeon systems, so in Xeon systems, you will not be finding the similar case. Xeon systems usually you will see that okay, they are somewhat 3.2 gigahertz, uh, or maximum that I have seen is I think 4.8 gigahertz or so, right? So that is the case. Murray's law, we have seen that the density, the transistor density increases doubles every 2 years. and that goes on and on. But again, rather than increasing the frequency further, because ultimately what we are interested in, performance per watt. So whatever be the performance per watt we would like to draw. So correspondingly, that is the main motto behind having the whole processor execution. So beyond a certain limit, it will not be possible to increase the performance per watt, and that goes on a constant node, or rather on a degraded node. So this is the basic concept. So there are few questions that should be there in your mind. So whether increase in transistor density increases the processing capability of the chip. Yes, anyone? Yeah, Manish, today's content will be part of the EC2, because when I was preparing the paper, so I don't want to miss the important contents of today's session. So that's why it will be part of the EC2, right? Yes, anyone? Whether increase in transistor density increases the processor capability of the chip.
At certain level, yes, but then it won't. Let us see.
Yeah. Again, what Ravi have said is correct. That at certain level, yes, when we keep on increasing the density, definitely the processing capability, that is the frequency ultimately, can be increased. But again, because the power consumption and the temperature will also rise, that will be difficult to control beyond a certain limit, and that's why beyond the limit it will not increase, and that's the reason why I am telling you again and again, so that at least you can remember. So 2001 gigahertz and 2025, even consider my system's processing, then also it is only 5 times, right? Not expected, as the industry is moving, or not expected with the pace with which industry is moving. But definitely there are limitations, and that's why we have to look for the alternate options. Okay. Whether Murray's law and the concept of multi-core are related with each other? Yes, anyone? Yuvraj?
Yes, they are. Till certain extent, Moore's law was true, and at one particular point in time where we figured out that number of transistors cannot be increased after a certain limit because of heat dissipation issues, uh, people started moving towards multiple cores instead of one core having more number of transistors.
Yeah, correct. So, Murray's law, where we can have the concept of multi-core, the both are closely related, in the sense that, okay, Murray's law states that, okay, the transistor density will double without much effect on the price every 2 years. The things continues, but when we witness that, okay, further increasing the density and trying to increase the frequency out of it is not making much of the difference in performance per watt. Again, that is the main entity, that is performance per watt. So that's why uh, they are related. Our modern generation processor is still limited to dual core, quad core, or octa core architecture. Anyone? Tanya, Jyoti, Gautam, Rahul.
Modern now it's multi-core, right?
Yeah, very good. So what Gautam has said is correct. not dual core, quad core, or octa core. Rather, we can say multi core in the sense that, okay, nowadays, if we are having i5 systems, that comes with 10 cores. Say it be i7 systems, that comes with 14 and above, say it be 20 uh, parallel processors or 20 cores. So that's why you can say that it is rather can be called as multi core. Right. And which of the
Sir, one
following technologies were developed?
sir, one
Yeah,
sub question
Yuvraj.
on earlier slide.
Yeah,
We don't have
Yuvraj.
limit on how many cores we can have. So what kind of limits the higher order number for number of cores?
Limit again, that will be decided by the overall architecture in terms of the motherboard support. Not only that, mostly limited by the cost as well. Right. So again, if you are increasing the cores, then in that case, definitely price will be increased. If you see the configuration of Xeon processors, so
Mhm,
corresponding to Xeon processors, you will be having many cores. Recently,
mhm,
I have witnessed one Xeon processor that was having 32 cores, and even 64 cores Xeon processor was there. So it's not like that we cannot increase the number of cores further beyond a certain limit.
mhm,
Uh, 64, I have seen that, okay, in Xeon we have seen the 64, and with the help of clusters, say it be if we form a GPU cluster, so through that GPU cluster and with the use of virtualization, right,
mhm.
we can have a system by pooling the number of cores. Right, so I can pool 64, 64, and ultimately I can have a 128 core uh, cluster.
Yeah.
Even with
Yeah.
GPU, thousands of cores we can.
Yeah, Ravi.
Even on GPUs, we can have thousands of cores, hundreds and thousands of cores.
GPU, Ravi, the concept is totally different. Definitely, what you are saying is correct, that the number of cores will be huge. Uh, Thousands is the right thing, means because that works on SIMD.
Yes.
Mm,
Right, so
mm.
single instruction, multiple data, that okay, something similar kind of thing needs to be done on multiple data. So that's why having the number of cores on a higher side will not affect much of the thing because the instruction is single and the data on which we have to operate is somewhat more, right? So that's why.
Yeah, in terms of I mean having core in a single chip, I'm referring from that perspective.
Yes, 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 yes. Correct, correct. So that way we can have the analogy or some practical thing again. But look at the pricing. When we are having the number of cores more, ultimately the pricing is huge, right?
Right. So
So
the way we like see pipelining, intent of pipeline was to increase the throughput, right? So
yes,
that does mean if we have more number of pipelines or pipeline stages, I would say, we'll have more throughput. That would be the idea. But that doesn't mean we keep on breaking pipeline into smaller pieces and increase the throughput that way, right? It got limited because of certain other reasons also, wherein we said, let's say 15 or 20 stages at max are good enough. Beyond that, we don't see a performance improvement to a certain degree, as in it
correct, correct.
flattens out.
Yeah,
On
yeah,
similar lines, if we just keep on increasing course, probably there would be something which is going to limit us, stating that after this particular point, even if I increase number of cores, that's not helping my performance. Is there similar analogy applicable in case of cores also? Price is one factor, agreed. If we increase, price is going to go up, but the original intent of it gaining more performance via increasing cores, Is that
Yeah, correct.
is that also in the context? Is the
Yeah,
question.
yeah, obviously it is in the context, and I think by all the logics we have developed till now, that this can be answered. Yes, anyone, if you would like to answer. So his question is that if we increase the number of cores beyond a certain limit, so whether we will be able to, one thing is somewhat on a programmatic aspect, and second one will be on the capability aspect, right? So ultimately the thing is, say it be if you keep on increasing the number of cores, okay, the thing is, the operating system that is being written, or the hypervisor that is being written, or whatever say it be, the compiler that is being written, the system programs, and ultimately if they are not able to utilize the number of cores that are being there, means whatever be the parallels that we can achieve with the number of cores available, if we are not able to achieve it, then definitely means we will means even the course will be there, but we may not be able to maximum have a maximum utilization of those cores, right? So first thing is there may be some limitation within the programming or the assembly language, or the machine language that we may be having. So that in that case, ultimately we have to deep dive into the machine language as whether there will be any limitation in terms of the number of cores. Other is the capability of the stakeholders, right? Let me give you an example for this. So the NVIDIA H100 NVL that I usually quote all the time, because we are having this GPU cluster, right? So corresponding to this cluster, what happens is this GPU. So altogether, we are having four such GPUs. Each GPU is having a capability of 94 GB. Okay, and corresponding to this, seven slices can be considered, right? So we can have seven mixed slices. Altogether, when we create seven mix slices, they were 12 GB of space, around 12 point something GB of space corresponding to each of the mix slice. Okay, so when we do the mix slicing, so I asked to have seven slices altogether. Okay, but when I handed over to one of the startup that okay, now I have created these seven slices. Out of this seven mix slices, you can make use of four mix slices, right? Because the VM that we have created, within that VM we have taken, or we have considered only four mix slices for his virtual machine. The problem was, even when we have given him the four mix slices, he was not able to utilize the capability of the four mix slices because he was not able to write the parallel programs so that to use the four mix slices individually, right? So he asked me that can he have a combined one, that is four mix slices combined with a capacity of 40 GB, so that whatever be the program he is writing, so those can be put over this 48 GB, right? So ultimately it's the capability of the programmer as well. So beyond the limit, if you witness that your operating system is not at all utilizing the increase in the number of cores because they have not considered it within the whole operations, then it will not have any kind of impact, right? As far as hardware limitation is being considered, definitely a threshold may come, because if you keep on increasing the number of cores, somehow beyond a certain limit, if you go, then again the same problem of heat dissipation and this performance per watt will be there, right? So that way, again,
Yeah,
the
yeah.
industry have to
Mm.
balance it.
Yes, yes, that helps,
Yeah.
sir.
Okay.
Thank you.
Yeah. Okay. So this is just the recap of the first few sessions we have gone through: the system configuration, the performance core, efficiency core, and the various specification of the processor. And in single core processor, we are having a CPU chip, and within the chip itself, we are having the arithmetical logical unit and other things. In multi-core chip, we are having multiple cores, and corresponding to each core, we will be having a equivalence corresponding to a single processor. Say it be, if you see that here there is single ALU, where here we are having multiple registers corresponding to each core. Not only this, we will be having the RAM, the cache as well corresponding to all the cores. So earlier, when only two levels were there, so when we were having, I think, dual core processors at that time, it was two levels. So their L1 is being individual to the cores, and L2 was shared. But when the third level is being introduced, so L1 and L2 was part of the main course, and L3 is being shared, right? So multi-core, you can just have a look, L1 and L2 cache, right? Mm, we'll just have a small video. I'll see if I'll share the screen again.
Sir, we are not
right?
able to hear you. Okay.
Yeah. So the main purpose is to combine all the keywords that we have seen till now, right? So one is hyperthreading that you have seen, right? Other one is the turbo boost that was there, the multi-core system. So altogether, by having this video, I think you would be able to connect all the keywords that we have seen, right? So quickly we will go through the basic definitions. So multi-core, integrated
Sir,
circuit.
your screen is not shared for me, and I didn't see video at all. Not sure
Oh
about
my
others.
God.
No, no, screen
Okay.
is not good.
Okay. Sorry for that. Okay. I have shared it, but don't know. So it
Your screen is
quickly
coming through
see.
now.
Yeah. Yeah. So I'll increase the speed at least.
Original size. Sisters, in order first 20 times smaller than my original. That's right, Mark. That is. Get small. Let's do it. And I love what you've done with my transistors. Where to first?
Let's head over to one of the CPUs. I mean, even as we integrate more and more technology into the die, the central process unit is still functioning as the real heart and soul of the microprocessor. And third generation Core features the most advanced CPU we've ever made.
Hey, looks like we got ourselves a quad core.
That's right, and in addition to the 4 CPU cores, it also has hyper-threading technology. So this microprocessor can be working on 8 instruction threads at the same time. And look at that, the turbo's kicking in. Along with hyper-threading and core parking, it helps the processor actually manage its own resources so it's constantly reconfiguring itself to make whatever you're doing run as fast as it can. And when it's not needed, the processor puts itself to sleep to save energy.
And is that the Intel Secure Key over there with the Intel OS Guard?
Good eye, Mark. Intel Secure Key features a digital random number generator to make encryption stronger, and Intel OS Guard helps protect against a hacker trying to take over your system. Third generation Core will be the first microprocessor ever to put all these security features right on the CPU.
Say, Brad, did I mention that we have to return back to our normal size before this counter hits 0?
No, I don't believe you did.
Well, now you know. So let's head over to the power control.
That is control. For instance, even though turbo and hyper-threading are implemented on the CPU, they're actually monitored and managed by the power control unit.
And this is also where core gating gets managed, right? Which means the PCU is in charge of how resources get.
Right. So this was the main thing. Sorry for that. I don't know. Means why even after sharing it doesn't happen because it was not shared. I think you may not be getting the voice as well, the audio as well. Okay. So
That's
this
true.
was the thing that ultimately multi-threading, then multi-core, turbo boost, and apart from that, the power control that not only frequency, but the power control unit controls the frequency as well. And the Intel Secure I that happens to be one of the security measures at the processor side itself, right? So that was the case. Now we will quickly go through the multi-core definition. Uh, I think now you have got the glimpse that ultimately it's a integrated circuit and where rather than increasing the performance, increasing the frequency further or going with a single core to be on more complicated side, we will try to have the same density, but within the same thing, we will try to have multiple cores somewhat similar to a single processor. So one core will be equivalent to one processor, right? And this all is being done for enhancing the performance and reducing the overall power consumption, right? So dual core we have already seen, and in within the same chip, all the cores will be there, right? Then just have a look at issues in the multi-core.
Sir, one question.
Yeah. Yes, Ravi.
in your earlier slide, somewhere in diagram,
Yeah,
it was showing where you have shown the multi-cores and all. Yeah, this one,
this
yeah,
one.
the
Yeah.
ALU, no, no, previous one, ALU and all showing, right?
Mm.
Yes. So each core will have their own ALU also. It is a common ALU.
No, no. Arithmetic logical unit will again be separate.
Hmm.
Uh,
Yeah, it
just
will be separate, but
imagine that it will be a single, somewhat equivalent to a processor, single processor.
yeah, because in a recent slide, multiple slide, you mentioned that considering each core as a single processor. So when we say processor, processor is combined of ALU and the control unit and all, right? So in this case, core and each core will have their own ALU, or this ALU representation in that diagram is just a representation only. So
No,
ideally,
no,
there
no.
will
It's
be
not
one.
a representation. It will totally be equivalent to a processor. So that
Oh,
way
okay. So
ALU will be
that
different.
that
Yeah.
means it will have its own ALU as well. Each core,
Yes, yes, yes.
each
Yeah.
core. Okay, perfect.
Otherwise, just assume that logically how difficult it would be if I'm having a common ALU, and then that ALU needs to be controlled by multiple cores. So things will be difficult to manage.
Hmm. Got you.
Okay. Yeah. So dual core, having multiple separate processors. Okay, you might have confused with this, right? But
Yes, yes,
processor
correct.
in the sense that we are saying that suppose I'm having the single processor, so that is being embedded within it, right? I'll still see the authenticity of this statement, right? Again, because the two processors are placed in the same socket, or rather within the same IC or the chip, right? So the connection between them is somewhat faster, right? And as Yuvraj has pointed it out, that if we keep on adding more cores, so that will not guarantee the performance improvement. So whatever we have predicted, because I was not recalling this particular slide, but that was only out of logic, that obviously the softwares and the OS written over and above the hardware must efficiently be able to utilize the number of cores. Then only we will be able to have a justice with the number of cores increased. Otherwise, it will be all in vain, right? And obviously, it's not direct multiple. That if you are doubling the number of cores, then your performance will double, right? So these are all the use cases corresponding to multi-core. And one best thing that we derive out of multi-core is the virtualization, where we can virtualize the things. We can virtualize the cores, and we can have the virtual machines with different cores, right? So these all will be the advantages and disadvantages. You can go through it. Multitasking will be increased, higher overall clock speed. Rather than clock speed, I'd prefer to say that, okay, higher overall performance, right? Then fault tolerant, because now we are dealing with the parallel system, so that's why somewhat fault tolerant in nature. Intercore communication, energy efficiency, and definitely bottlenecks will be reduced if we are having multiple cores, right? So these are some of the architectures of
Sir,
multi-core.
one question
Yes,
on the
Yuvraj.
clock speed. Can you, yeah, just hold
Yeah,
here.
yeah,
Now, the clock which will be used by all the cores, that clock is going to be exactly same, right?
yeah. That clock will be same,
Okay, so as you said rightly, clock speed is going to remain same, but
same. Yeah.
the work which we are going
Overall
to,
performance, yeah.
hmm,
Rather than clock speed, we will be more abiding to the overall performance.
right?
Yeah.
Because the work, see, like every processor or every core will contribute to work, the work would be done in a faster way, effectively increasing the performance. But clock is going to be shared
Performance.
across all of them.
Yes, yes.
Okay.
Okay. So now there are multi-core processors. Yeah. Types, you can have a homogeneous or you can have a heterogeneous, right? So homogeneous in the sense that, as the name suggests, uh, will remain same. Every core will be having the same capability, while heterogeneous, where your cores may be having different capabilities, just like in mobile systems. If you have ever seen to this level of depth about the processor, so mm, now onwards, if you see any mobile phone, I have seen it at least in Android, right? So few of the Android phones, just like OnePlus or even anyone that you can pick up, just see the various cores corresponding to their processors. So we'll be finding that okay, one core is operating at 3.1 gigahertz and other may be operating at 2.8 gigahertz. So I've forgot to include any snip of the mobile specification, but this is very common. Means if you search for any of the mobile specification, and if it is multi-core, which is a common thing nowadays, so when you deep dive into it, you will find that okay, they will be highlighting the higher frequency that okay, this processor is a Snapdragon processor coming with 3.1 gigahertz. But nowhere in the advertisement it will be revealed that okay, there is another core, the another core will be operating at a lower frequency, that is 2.8 gigahertz. So this is again very much possible, right? Multi-core versus
Sir,
multiprocessor. That's quite
sir,
obvious. Yes, Yuvraj.
sorry to interrupt again.
No, no, no.
Uh,
Don't be sorry. Yeah, come on.
Homogeneous and heterogeneous. Now,
Yeah.
having all cores homogeneous makes sense, but what in which use cases or how heterogeneous combination helps us?
It will not help the end user. It will help the manufacturer. The example that I have given you, they will be highlighting the higher side, say it be 3.1 gigahertz, but at the same time, they may have to manage the cost or so. So
Mhm.
that way, not only cost, but again, the battery consumption, and I think that is one more reason because even turbo frequency is there still if they would like to restrict it that okay, whatever be the applications that are there and that will come, if considerable performance can be witnessed, then what exactly is the reason to go with the same kind of processors in all the cases, right? So that's why to balance the cost, the performance, and everything, they may be having a choice. So it's advantages for them rather than for the end user.
Okay, probably end user wouldn't even understand that there are cores which are of heterogeneous.
Not
So
even understand. I think many
no.
of even techie may not be knowing this, that this is happening.
Okay.
Yeah. Right. So now whenever you will see any mobile specification, just try to see the various cores and the frequency at which they are operating. So multi-core versus multi-processor, quite obvious that in multi-core we'll be having a single chip, and within that chip itself, all the cores will be there, and that's how we are terming it as multi-core. While in multi-processor, the motherboard will be having the capability of accommodating multiple chips. Say it be if a dual processor is being there, so in that case two processors will be there on the motherboard. Generally happens with the server systems or when you are having some cluster getting ready. So that time you usually have some motherboard with two processors. That was the main convention in earlier days when the multi-core option was not there. So at that time it was very popular. And nowadays it's being utilized only in servers. So in servers, so you can have the difference between multi-core and multi-processor. right? The visible size of the processor, dual core or Intel i7 is almost same. So where are the extra cores accommodated? So just think over it as what exactly will be the case, and we'll be discussing it in the next session. But at least some brainstorming should happen. So please have a 3 minutes break. We'll resume at 9:43. Okay. Okay, resuming the session. Now we have seen multi-core, we have seen multi-processor, okay, and pipelining. Now the next version where we can increase the performance is the GPU architecture. So just have a look at the diagram. I think it will summarize the whole concept. What exactly is GPU? So you are having some traditional configuration where CPU is there. Then instructions are coming to GPU from CPU, and the data is being transferred from system memory to GPU memory, right? And ultimately, the processing will happen. And once the processing happens, after that, we will be having the final output in a uh, proper way or in a speedy way rather, because the as Ravi have said that ultimately the number of cores within the GPU will be huge, and because of that, whenever similar kind of task needs to be done in a parallel way, it would be very favorable that rather than getting it done through CPU, can we get it done through graphic processing unit, right? So ultimately, it is designed initially for the graphics rendering or so, but later on, when the overall concept was seen related to SIMD, where single instruction multiple data is to be operated, so it was equally utilized in the similar concepts that of graphic rendering, just like video processing and machine learning as well. Because if you see the core of machine learning, then in machine learning itself, you will be having the same thing. Ultimately, you will be having ample data that need to be operated or processed so that you can come up to some kind of model or conclusion, right? So that way, as an extension to the graphic rendering to video processing, ultimately nowadays uh, the new generation sees it more towards the machine learning aspect rather than its core reason for which it was invented, that is the graphics, and that's why it is called as the graphic processing unit, right? Ultimately, it uses single instruction, multiple data that I have iterated again and again to perform parallel operations efficiently. Okay, so as such, SIMD comes as three variation within the architecture. It can be a vector architecture, it can be a multimedia SIMD instruction set extension, or it can be in terms of GPU when we it comes to parallel performance processing. So we can handle these three. Among this, we'll be concentrating more on the GPU, where hundreds of floating points or now we can say thousands of units are responsible for high performance, right? So if we try to figure out the differences between the two, then definitely one difference has already been pointed out by Ravi, that the number of cores will considerably be differentiating. Say it being CPU, it will be somewhat limited, while in GPU, because the purpose is totally different. If you have already pointed it out, then the purpose is different, where in CPU, we are not restricting it to a type of instruction or single type of instruction. It's open and any type of instruction, any number of instructions can be executed. While in GPU, our sole concentration is on getting a similar kind of thing uh, that can be done in parallel, so that once it is being done in parallel, later on combined to either generate a image or either to give the final result of the data processing that happened through machine learning. Right. Obviously, next is the memory construct, the cache layer, memory controller, global memory, and all. This will be different. So I'm preparing a animation, so that way these all things will be more clear out of it. Today we'll be going through the concept at least, so that it will help you out in AC2. Sorry for this. And control unit. Definitely there is difference in the control unit as well. Okay, so CPUs, they are designed for running a smaller task of potentially a smaller number of complex tasks, while in this case GPU will be having running a large number of simple tasks in a parallel way, right? So that will be the main concern. And here in CPU, we'll be having a small number of registers per core. Here we'll be having single set of registers, but with multiple banks or with multiple what we can say storage, right? So we'll see. So this is CPU we have already seen, and this is GPU. You can see the number of cores, then the PCI, the RAM, GDDR5 RAM, the memory controller, right? So this is just a comparison in terms of number of cores. So you can just have a look. If I have taken only Titan V, I haven't considered the recent GPUs that are there, but you can see that the number of cores here is 28, here it is 5120. Threads, the hyperthreading that we have seen is almost it goes to 2 per core, not more than that when it comes to CPU. But here just see that internally GPU one core can be considered as 32 threads, right? So that's why it means there is a difference in pricing as well, because and altogether it's a monopoly that happens, right? So you can go through the rest of the specification as well. Okay. So CPU, because ultimately whatever be the system that was set will remain same, where CPU will be responsible for initiating the computation, right? Once the computation is initiated, the data or whatever be the graphic data, whatever be the processing data needs to be sent to the GPU that is being transferred. So after that, the control will be taken by the GPU and CPU can continue doing rest of the work, right? So beginning and end of the computation will require the intervention of CPU, and somehow we will be requiring access to input and output devices when we are having some input and output corresponding to the GPU operation, right? And there are some ongoing efforts so that API can be developed so that we can provide IO services directly on the GPU, right? So ultimately, the whole industry needs to be in sync for this, but because everything is being initiated by the CPU as of now, so that's why the things are being initiated by the CPU, handed over to GPU, and then whatever be the result, GPU is ultimately handing over to the CPU again, and then IO devices are being somehow involved through the CPU. But efforts are being there where can't we have the input and output directly with the GPU so that whatever be the latency that is being generated or that is there with the utilization of processor can be avoided, right? So that's why the final concluding statement that it's not standalone yet. You cannot have a system having a single GPU without having a CPU, right? Okay, so GPU, as I told you that initially they were designed to quickly create and display 3D images because ultimately the core concept remains same. Say it be if I'm having an image, so corresponding to that image, I just have to pick the pixel and do a bit of modification. So that way, the basic concept will remain same in all the cases when we will be generating the 3D images. And at a later stage, when it is it seems advantageous with respect to other applications of machine learning or any other application that can be parallelized. So that way, GPU was there. This is just a good example that I found, right?
So
So just
ideally, GPUs are like, even though earlier they were used for the graphics and all, but
yeah,
in a nutshell, they are actually doing the matrix and vector calculation.
correct, correct. Uh, I think this example
And
will clear it further. Yeah, Ravi.
no, no, sir, nothing.
Yeah. So this is just a 2D diagram. Say it be if you say that normally the wire structure is there. Okay, so you can have the description of the surface material, light, camera, and again, if you would like to draw that how exactly it would look like, right? So this image may be needed to be generated. If this is the input, then for generating this as the output, I think you can assume that if it is being divided into mesh and now each of this mesh is to be converted into the respective thing based on the various parameters, right? As from where the light is coming, as from say it be if this light is being there or this is being there, so it will be reflecting somehow over here. So based on the basic information taken as an input, rest of the things almost remain same. Um, because ultimately we just have to fill it on a parallel note, and if it can be done in parallel way, so we can speed up the process drastically, right? So this is the case. So that mesh is being filled based on the input, the respective pixel can be picked, and ultimately the overall image can be generated, right? Okay, so earlier the at very beginning, say it be 2004 to 2010, it was your graphic accelerator. Um, Primarily, they can be called as graphic accelerator, but now with the involvement of machine learning and utilization of these GPUs to these machine learning approaches, right? So you can say that okay, they are some HPC cards rather than the GPU cards, right? So this is the basic architecture. These are few of the diagrams. Right now, types, if we call on types, then it can be integrated that you usually see in Intel. So within the chip itself, you are having a graphic processing unit, a fully integrated GPU. Uh, Allows for thinner and lighter systems, reduce power consumption, and lower system costs. So ultimately, if you see my systems, then you can see that two GPUs are there. One is this, that is Intel Iris Xe graphics. So this is again 16 GB. And the another one is NVIDIA GeForce RTX 3060. So this is the another one, that is discrete graphic processing unit. Right, so this is 6 GB, and the earlier one, the integrated one is 16 GB. Right, so discrete graphic processing unit. You can say that the NVIDIA card that is being utilized, right? And you can have the third variant as virtual GPU, where say it be if you are having some software-based graphic processing unit. So that way also you can have the GPU, or the other definition can be the slicing that we usually utilize. The example that I have given corresponding to H100 NVL.
Sir, I have one question. Previous
Yes,
slide.
Gautam. Yeah.
So here, integrated versus discrete. So discrete is outside of the chip. Is it a separate device we need to connect?
Discrete is
Or
NVIDIA directly, matlab preferably it is on the PCI slot.
okay, okay.
Yeah.
Separately, I mean, as a socket, we can
Yeah,
install it and
separate
use it.
slot.
Okay, okay.
Yeah. So you can see
On the
that.
motherboard, these slots are PCI.
Yeah, PCI slot, and within
Mm-hmm.
that, your graphic card will be there, while
Okay.
this will be integrated within the chip.
So I have one question.
Yeah,
I
Ravi.
mean, when we are, let's say, when we plan to buy any laptop and all. Now,
Yeah,
integrated graphics anyway, I understand because there are lots of internal graphical applications or GUIs and all. It requires for that. Now, let's
yeah,
say uh, as a layman person, every person have an analogy. Okay, if I add the NVIDIA card additionally, then my it will boost up my the performance of my laptop and all. And then
yeah,
people go on that way, right? Right. So
yeah.
how? Actually, it is true. Actually, so my understanding is, if until unless we use those kind of application which require like graphical or gaming and all, which require GPU, until that that is not going to give any kind of performance boost up. That's my
Correct.
understanding. So,
Correct.
so
Correct.
is it something, if I'm not using any gaming or I'm not using that, so will that additional card help me in some way?
Mm. In some cases, I'll just give a practical example. So recently, one of my colleague, he was attaching a display, right? So an extended display he attached, and after attaching it, the system goes a bit slow. Not a bit, it goes considerably slow, means the mouse pointer was moving with a slower pace and all that. So in such cases, when you are attaching the display, the TV was attached altogether, the video has to do much of the processing. The video card has to do much of the processing, and that's why the overall process gets slower. On the other hand, when I attach my system to the same television, so that time there was no lag because of the GPU I'm having. But what you are saying is very much correct. Until and unless they have the use. Why I have bought this particular system is because I used to do the virtualization as well, having the multiple cores and all that. Apart from that, a lot of graphic applications, just like the Photoshop and those applications are being utilized. But what you are saying is correct. Until and unless you are having a specific reason, say it be if you are not doing any gaming, or if you are not doing any graphic, working on any graphic application or so. So having an external GPU card is all in vain, means not at all required. You will not be able to even utilize it. Again, we will see it by the performance itself. Now just have a look. As of now, even when the graphic display, an external display is attached here with the utilization, the overall utilization of the GPU is only 2%, right? While this is being utilized, the integrated graphics is being utilized 13%. So, as such, as of now, it is not making much of the difference. Right? But again, what I told you, that utilizing Photoshops for creating the
Mhm.
images for the presentation and all that, at that time when you will see this GPU, so definitely the utilization will increase.
Now, on the same question, just adding the example of MacBooks.
Yeah.
They now recently with M4, M3, M4, M5,
Hmm.
it is mentioned that they processor M5 coming with a 10 CPU cores or
10 cores, yeah.
10 GPU cores and all. So in those cases, those GPUs are actually the same which is mentioned here is like integrated GPUs.
Yeah, they
They will
will
work with the.
be integrated. Yeah.
Okay. Hello.
Yeah. Okay.
Sir, one
But
question
that
on
is a good
integrated
question.
versus.
Yeah, yeah, Yuvraj.
Sorry, can you go on earlier slides?
This one?
Integrated versus the discrete. Yeah.
Yeah.
Now, if we consider integrated graphics processing unit, then basically operating system while getting initialized, it will understand that integrated graphic processing unit is there, and then it will be able to use it efficiently, right? As an
Yeah.
application user, or we won't worry about whether GPU is getting used correctly or not.
Hmm.
So having it integrated is kind of something that setup is there or mechanism is there already established. But when we add discrete graphics processing unit, how does it know how efficiently the discrete graphic processing unit can be used? Because it's optional, right?
Yeah, it's
So
optional, but it is in the scene. Means it's not out of the scene, even when it is optional. So
Mm-hmm.
whenever the operating system is being coded, so at that time you should be having a vision that okay, if through the PCI slot, because ultimately the driver will be installed and the whole communication is being established, and that's why once it comes to OS, that okay, the OS knows that okay, there is an NVIDIA GeForce RTX attached to it. At a programming level, whatever be the controls given by the GPU, all those controls will be available to you.
No, I
Okay,
think
so
nowadays the programming framework also coming with this kind of supports where
Yeah,
intention
yeah,
if you
where you
want we
can
can engage.
specify the
Yeah,
cores as well.
yeah, even
If you
specify yeah
recall,
threads and
then
those things. Even
yes,
last
yes.
semester only it was there in our course also. Same distributed and parallel computer.
If you
Either we
recall in
can.
an initial session also, I have told you that nowadays we can program it and
mm-hmm.
specifically not GPU, but I have specified it
Specific
for
core.
CPU
Mm-hmm.
cores. That you can specify that okay, now these many cores can be utilized to this program, and that kind of control is also available.
Okay, so
Okay.
operating
Sir,
system will
one
have a mechanism
Yeah, yeah.
stating if
Bridge.
GPU is there, then use it this way. If it is not there, then get your work done via CPU,
Yeah,
kind
yeah,
of a
yeah.
thing.
Yes, yes.
Okay,
So
okay,
operating system will be the bridge.
okay.
Okay. So there are several architectures as far as NVIDIA is being considered nowadays. You may be uh, hearing that Blackwell architecture is getting very popular from NVIDIA. So the animation that I'm creating will include this as well, the various architectures. But for the timing, just see that these are all the architectures from NVIDIA, Fermi architecture, Volta architecture, and apart from that, Blackwell architecture is again there. So this is the whole journey of the GPU architectures. So I'll correct it. I've written it processor architecture, but it should be the GPU architecture. So Calvin, Kepler, Maxwell, and nowadays the popular is the Blackwell architecture. So nowadays, whichever be the GPUs that you will see, say it be 6000 or so, so all those are coming on the Blackwell architecture. Again, stick to the basics architecture in the sense that okay, somehow there will be the difference in either the overall concept of the architecture that we have seen, where either you are changing the address bus or whether you are changing some of the architectural feature rather than the organizational feature, and that's why it is being said to be change in architecture rather than change in organization, somewhat similar to our Xeon and all the processors like i7 and all them are based on the same architecture, but here uh, the architecture is differing rather than the organization, right? So Calvin Blackwell architecture, right? So these are the specifications. Don't have to go into much of the detail, but uh, I think the animation that I'm creating will include much of the differences. CUDA, so Compute Unified Device Architecture. So the basic challenge for GPU programmer was not simply getting good performance on the GPU, but also for doing the appropriate scheduling, right? And to transfer the data between the system, memory, and GPU. So that way, if you would like to efficiently utilize the NVIDIA GPUs, so this particular compute unified device architecture, that is CUDA programming, can be used. Okay. So OpenCL will run on CPUs and GPUs from many vendors. right? While CUDA will only run on NVIDIA GPUs. Yeah. So this is just added. We don't have to
One
do
question on
involve
the
into the programming. Yeah, Ravi.
hello. Yes, one more question on the this framework part, like programming framework.
Yeah.
So with the integrated GPU which comes with, can
Hmm.
we create? Can we program using those GPUs? Like
Program in the sense,
like example, if I don't have any NVIDIA card. Now there
yeah.
is always an integrated GPU, right? So if I use any OpenCL or something, can I use those GPUs in use that in my code?
Need to check means directly I cannot answer this. I need to check that whether we have done it through NVIDIA because
Hmm.
all the time we had those. Even in my laptop,
Yeah,
I'm
NVIDIA
having one.
anyway, we can use CUDA and all.
Yeah,
So,
yeah, yeah,
so
yeah,
let's say I don't have any NVIDIA, even now I don't have any external GPU card associated, right?
yeah.
But
So
still, motherboard CPU comes with the some GPUs, right? Integrated GPUs
yeah,
and all.
yeah, yeah.
So I was just checking if
So
we can
need
use
to
from.
check that whether we can use it for the programming purpose or it is being utilized by the processor itself only for the internal
Hmm.
operations, right? But we have done it through
Okay.
NVIDIA a number of times. Need to check whether we can utilize, but never it was the need. That's why I think never the question clicks into my mind. We'll check that and we'll revert on it, right?
All right, sir.
Yeah. Uh, Execution model. Now we can escape. So we'll quickly go through this and then we'll wrap it up. So this is the basic execution model. You can see that CPU memory is there and apparently the whole instruction is being initiated by the CPU. Whatever be the data that is being copied from CPU memory to GPU memory, then that GPU program is being loaded and executed within through the CPU. Whatever be the caching data and other things are there, that is being loaded. Apparently, whatever be the results that is being generated from the GPU. Okay, so that way we can have it. So those results can be loaded again to the CPU and then been exhibited to the input output device. If it being an image, that image can be made visible to the monitor, or if it is some kind of results corresponding to the machine learning models, so it can be the other way around. Okay. I don't know whether you have gone through this video or not, but let's see.
All right, I introduced to you Leonardo, and he's
Have
going
you
to...
seen this?
Yes, yes. You see. At
All
least
right,
one
I
minute.
introduced...
Okay. In your class, I have used this video, is it?
No, no, no.
So I have not seen
Independently,
that.
as I said. No,
Okay, you might have
independently.
seen it
All right, I
personally.
introduced
Okay.
to you
Yes, yes.
Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed. Ladies and gentlemen, Leonardo 2.0. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration
Yep.
in 10,
Nine,
9, 8, 7, 6, 5, 4, 3, 2, 1.
Right, so this is the difference. Means I hope you have you can connect both of this image and video. That apparently the whole thing is being transferred to GPU, and because GPU is having multiple cores and capability to work on similar kind of thing in a parallel way, so that painting was ready instantly rather than doing it one after the other by going through few of the cores of CPU. So once it is ready, it is being transferred again to the CPU memory and whatever means it output also apparently. So this is just the analogy that is being displayed through the video, but you can correlate it. Okay, so this is the sample program, supposedly not specifically to GPU cores, but just to show the difference that this we have used for uh, because we were using one display and at the parallel time MQTT is to be utilized. But when we were not allocating a specific core of that ESP32 to display, so there was a considerable lag, right? So that's why we have provided a specific display, one specific core to display task within that particular ESP32, right? And this way we can include the CPU cores, right? At the same time, supposedly graphic card is to be specified. So this is one of the setting available within the Windows operating system through NVIDIA control panel. So you can see here, I can choose on the application, say it be Adobe Acrobat, and I can see that which particular graphics to be utilized. So whether NVIDIA or whether integrated graphics. So this is your integrated, or you can choose that, okay, high performance NVIDIA. So when this particular application is being utilized, which to choose, that can be made or that can be decided on this particular NVIDIA control panel, right? Next is massively multi-core, but this will not be part of EC2. So that's why means I'll conclude over here. Altogether, my philosophy is that if I'm having less number of questions, so things will be difficult from your side because in that case, providing numbers or giving numbers will be tough from my side, right? So that's why altogether there will be 7 questions, right? 10 from each of the module. One is the cache, another one is the processor architecture, the architecture organization part, and third one is this one, the instruction set architecture, almost equally divided with a complexity of 30% will be the analytical, rest 30% will be direct, and 40 will be the moderate complexity questions, right? Be specific in the sense that if 2 mark question is there, then just write accordingly. Don't think that, okay, within 2 mark, if you write more, then that will be replicated in another questions. No, that will not happen. So a
Sir,
2 mark question can be answered according to its what I can say, the intensity or whatever be the requirement. Okay. Yeah, Gautam.
um, any rough high-level ratio, I mean, numericals versus the theory part
One
in exam?
numerical will be there in both
Okay.
what I can say, regular and makeup.
Okay.
when
On
numerical
the
will be there.
okay. Majorly on the
Anything
numerical
means
side.
in most of the
On each section,
cases.
you mean, right? The three modules you mean.
But overall one numerical, not more than one.
Okay, not more than one.
It can
Uh,
be from cache, it can be from
Okay.
the architecture we have seen, say it be. Uh, that I can recall that MIPS, or it can be from the Amdahl's law, if not numerical, but at least some inferences related to the formula that may be there.
So
Okay.
today's content is also the part of midterm. Today's
Yes,
contents.
Jyoti, when I was framing the paper, I was finding it difficult not to include, so that's why I have to include.
Is still module 3
Yes, yes, it's
complete.
still module 3. Yeah.